Morning, everyone. This is Uma. Thank you for joining. Welcome to OpenEBS Hangout number 4. This is the general agenda that we'll be following today. Feel free to ask any questions in the middle on the chat window, and we will be glad to answer. So there are actually a couple of demos. One is Maya Online, the SaaS platform demo, which I'll be doing. And then our CTO, Jeffrey Molinas, will be talking about CStore and a tech preview demo of CMotion. And then we'll open it up for questions. With that said, let's get started with Maya Online. Before we get started, just a small update. The sponsor company of OpenEBS project, CloudByte, has been renamed into Maya Data. And we also released an alpha version of a product called Maya Online in KubeCon. And Maya Online is a cross-cloud control plane for OpenEBS installations. Users can use OpenEBS to support the storage for stateful applications. And then with the latest release, users actually have Prometheus and Grafana support on the local OpenEBS instances. But as they start using multi-cloud phenomenon, you will end up in using OpenEBS across clouds, and that's where Maya Online can come in as handy as a centralized visibility automation platform. It also offers chat ops, and in return to the metrics uploaded from the user's installations to the centralized Maya platform, Maya actually uses machine learning and then tunes the OpenEBS installations to run the workloads better. So it's a feedback cycle, and Maya Online is free for basic usage. It's right now invite only. As I said, it's a multi-cloud solution. OpenEBS installations, when joining at Maya Online, get a deeper drill down of their centralized metrics across the clouds into a nice Prometheus and Grafana based instances. And also Maya Online provides chat ops for better management. Currently it offers the alerts and basic configuration querying. And as it goes through the next version, it will have more functionality. And using Maya Online, you can actually move the stateful workloads from one OpenEBS instance cluster to another, or we can move from one Kubernetes cluster to another, even across clouds or cloud providers. That's really where we call it as cross-cloud data plane. And it actually moves the entire data online from one as a pod from one cluster to another cluster. So this is a unique feature that can be used to manage migrations or even multi-cloud solution. You can just move your entire application from one place to another place. Let me show a quick demo of it. So here is Maya Online, and I also have an OpenEBS cluster. Which is imported into Maya Online. I'm running a Percona application, and we have a Maya OpenEBS API server running on the cluster, and it has a Prometheus instance, Grafana pod, and a provisioner, of course. And we have a persistent volume claim being requested by Percona application, which is being fulfilled as a storage controller and a storage replica, as you can see here. and you can log in through your GitHub credentials. I have a predefined user. This is how it looks. You can see a multi-cloud Kubernetes clusters that are using OpenEBS in a single config monitoring plane here. And we have a concept of organizations. A user can define its own organization and then start importing clusters. And for example, all you need to have and to start with OpenEBS is running a Kubernetes cluster. You can import an existing OpenEBS cluster, or if you just have a Kubernetes cluster, Maya Online can install OpenEBS and import it for you. And let me show you how a cluster looks like. This is not a full config plane for Kubernetes itself, but this is a monitoring plane for OpenEBS installations. So you will only see the pods that are consuming OpenEBS storage. So as you know, OpenEBS actually is it provides volume as a full storage controller. So for example, here MongoDB is consuming one volume. It is presented as a full storage controller on two replicas. And you can actually see multiple granular capabilities like Prometheus per volume and Grafana per volume, analytics and alerts per volume. Now let me actually go and show a simple Grafana capability dashboard for the volume level. And so this is one active application that's running with one replica. Let me open up a Grafana dashboard. Let me just set it up for 1 minute and let me refresh 1 second. And this application I can let me start some stress test. So I've started running some workload on this volume, and as you can see, when you run the load on your local cluster running on one cloud, Maya actually picked up the statistics runtime online, and you can actually get very granular, detailed monitoring statistics on per volume level. So for example, you can actually see, this is pretty amazing, you can see the latency of a workload running on that volume, and we have configured it in such a way that it's a little bit high. You can actually see this is a 6-second latency right now that's being observed, and you would have got a Slack alert on it, and you'd be seeing that. So that's a small demo. For the benefit of time, you can, I'll go back to my presentation, but users can sign up right now, and will enable access on an invitation-only purpose. Hopefully, it'll be opened up to the users pretty soon. And with that said, let me also go back and start on OpenEBS. So are there any questions in the chat window? Okay. All right, let's move on to the next one. There may be some users on the channel who are joining or interested in OpenEBS for the first time. So let me take a few minutes and recap what actually OpenEBS is. OpenEBS, as you know, it's a storage solution, containerized storage for containers, and it's a solution for stateful applications which are running on Kubernetes clusters. And the main difference is instead of having one monolithic storage controller for thousands of volumes on Kubernetes, OpenEBS actually provides a full-blown storage controller per volume or per application or per team. That's the most granularity that any user can get to. And mainly, OpenEBS is integrated into Kubernetes. And if this is a Kubernetes clusters that we all are aware of, OpenEBS fits nicely into it. And OpenEBS runs the storage as a pod within your application. And the component, the orchestration helper component of OpenEBS called Maya, it schedules the volumes on minions, and it uses Kubernetes itself for scheduling. So all I'm trying to say is there is no additional scheduler components. It actually deeply gets integrated into Kubernetes itself, right? So how do you actually get started? It's pretty simple. All you need to do is just apply an operator through a kubectl, and it installs OpenEBS provisioner, API server, as well as some storage classes. And then as a developer, you just need to pick the right storage class. There are some templates that we have provided. The templates will be written on a per application basis. Choose your template which has the right storage class, modify the capacity quota and other things, and then run your application. When you launch your application, the persistent volume is provisioned by OpenEBS provisioner as a storage controller itself. As you can see, there is one controller running, and then there are two replicas. And the controller also has a sidecar here, which is the volume node exporter for metrics. And so this is OpenEBS volume architecture. For each stateful application, you're going to have a controller, storage controller, and then the number of replicas as defined by the storage policy. And I mentioned CStore here, which our CTO Jeffrey is going to talk, very soon. It's a storage engine being refactored for the highest performance near-line disk performance engine, which is written completely in Userspace. The current version of OpenEBS is running the Longhorn-based storage engine, and both will share the same architecture. You will have OpenEBS replicas, as many as you configured, and a full-blown storage controller attached to an application. So with that said, that's a quick recap, and let me just jump on and probably pause for a few seconds to check with Nishant if there are any questions.
Not for the time being, sir.
All right. Let's move ahead with release updates. The community has been great for OpenEBS, very, very supportive. The last few months, we had a very successful Hacktoberfest event where we gathered more than 50 PRs, and our contributors are close to 100 or a little more than that right now. And we are excited and proud to announce OpenEBS 0.5. Some of the highlights of this release are OpenEBS gets its own Prometheus Grafana capability at a cluster level, and OpenEBS has introduced a volume exporter at a per volume level. It goes as a sidecar into the storage controller that's attached to the pod. And the storage policies that you can set right now, or the number of replicas you can turn on and off the monitoring capability. And the biggest of it is we have introduced a policy called storage pool policy, using which you can start working with the underlying storage layers like AWS EBS or Google Persistent Disk or local disk or anything else that Kubernetes supports. So using storage policy, pool policy that OpenEBS 0.5 has, you can start integrating it. And we are doing more in 0.6 on the storage pool policy, which I'll talk about it in a second. But that's a great start. After running the storage controllers in a good quality manner, we have started introducing the storage policies, which is a real need for the DevOps admins and DevOps developers. So parallelly, we've been actively contributing to Kubernetes, and mainly we started off with contributing some of the capabilities to Kubernetes dashboard. Kubernetes dashboard so far had, mainly from the compute perspective, and we have introduced some capabilities to see the configuration of PVPVC, which was released recently with 1.8.0. So the code changes that have been contributed by OpenEBS are upstream in Kubernetes. And as you can see now, you can actually scroll down or maneuver through the PVPVCs in Kubernetes dashboard right now. And the next thing that we are contributing are the disk and network usage statistics of the volume or storage controller level into Kubernetes dashboard itself. This is in progress, and hopefully we'll be able to push this into upstream and get it pulled into upstream very soon. So what's coming in 0.6? Kubernetes has provided many new features from the storage point of view. OpenEBS Provisioner will be adding support for all these capabilities in the 0.6 release. And apart from Kubernetes extensions or support for Kubernetes extensions, OpenEBS is writing its own capabilities in disk monitoring alerts area. And we actually, whatever the storage policies that are introduced in 0.5, we are going to refactor into a full-blown storage policy engine using the custom resource definition feature of Kubernetes. And we're going to be able to upgrade OpenEBS using kubectl. And then there are some enhancements on debuggability and better CI to support OpenShift, CoreOS, Rancher, all will be part of OpenEBS 0.6. With that said, we'll probably take a small pause to check the questions and then hand it over to Jeffrey.
Hello. Hello.
Yes.
Yeah, Uma, I have a question from Rajesh Saibaba, and he is asking that I am new to DevOps and Kubernetes. If this question is silly, is OpenEBS can be run on S3 storage on AWS?
Yes, very good question. Thank you, Rajesh, for joining. We really appreciate it. A very good question. OpenEBS can be installed on any Kubernetes cluster. So if you are running your application on AWS, you can use the storage there, EBS storage, and attach it to OpenEBS through the storage pool policy. And then soon you will be able to use Amazon S3 to store the snapshots. So the idea is to help the DevOps developers and admins wherever they are, whichever cloud they are in, to get the storage policies in a granular way to them. Yes, you can definitely do it, and we'll be very happy to get started. We are on Slack, slack.openebs.io. Please join in, and we are all lurking there 24 hours. We'll be very happy to get started with.
Yeah, hello.
Yeah.
So we have another question from Viet. I guess we welcome Viet. Actually, he is from our OpenEBS users channel, and his question is, what kind of underlying file system that OpenEBS is using? For example, root.io is based on CEPH as itself, or OpenEBS is developing own file system from scratch.
Right. I will probably get Jeffrey to answer that question. He's the lead that's running the underlying storage for us. Jeffrey, take that question.
Yes. Can you guys hear me?
Yes.
Okay. So You know what? Let me see if we can circle back to this question after I've gone through my slides, because we are going to talk about that specifically in the next couple of slides. Would that work for you? And then we can circle back to your question and you can ask any question you want. Would that work?
Sure. I think thanks, Jeffrey. I think we will do that. We have not enabled mics for all the audience, but that should work. Thank you. And thank you, Vyat, for coming and being on Slack. And we are looking forward to help you get started. And thank you again. So over to you, Jeffrey.
Yes. So let me see if I have controls over the screen. Not yet. This basically, this section of the presentation goes into the underlying details of how we actually put the data from all those persistent volume claims on the disk. And I'd like to start out, and actually we call this project internally CStore. So today, OpenEBS comes with a Longhorn backend, or which we call Jiva today. And we are looking very much for a way to make this backend storage system pluggable. Now, the reason that we want to have this pluggable is because what is true today does not necessarily mean will be true, in the next 5 years. Technology is moving very rapidly in our space, so we want to be able to plug things in and out. And we started out with Jiva, and the next one will be CStore. And before I go into details in terms of what CStore is, I first want to talk about what it is not, and probably more important is explain why it is not. So what it is not is a distributed file system, and this is typically something that people think they need because they predict that they will have huge capacities into the petabytes, and they will require a huge bandwidth and a large number of IOPS. But distributed systems are also hard to manage in production. They require, depending on the size of the company, they can require a whole team to get the system up and running and get it into proper shape. So the other reason why it is not a distributed file system is because when we looked at the container space and the microservices architecture, we found that typically the volumes that people are using are very, very small. So they are usually in the gigabytes. Sometimes you have a petabyte, but never ever have we seen microservices using petabyte volumes. So we don't necessarily need this big capacity. So the other aspect then for distributed systems would be performance. So how do we get performance in CStore/OpenEBS? Well, as it turns out, hardware is solving that problem for us. We can have a single NMVE device deliver up to 400,000 IOPS, right? So, if you would stripe these two devices, you get a huge amount of IOPS. And not only that, but looking again into technology refresh, 3D X-Point is on its way, even making these numbers bigger, where we will have machines running into terabytes. Now, the thing obviously is that people, normal people like us, will not necessarily have access to these type of hardware directly, but our cloud vendors will. So when you're on Amazon, when you're on Google or what have you, you typically run on these modern type-like hardware platforms. So they will become available to you without necessarily purchasing them. The final reason why it's not a distributed file system is the cloud native paradigm that is being used to build application these days. So typically, modern day applications are already built at the application level to scale. This is the whole genesis of Kubernetes, right? Where you can scale up and scale down your pods as you move around the road during production. And because of the architecture of these applications, you don't need to scale at the storage level. So normally you have an application, it's a big monolith, it doesn't perform. What do? You go to your storage admin and say, hey, storage admin, I need more IOPS because my SQL queries are taking 2 milliseconds or whatever, right? Data migration happens in the background and hopefully performance increases. These days, all of these cloud systems have load balancers built in, HA proxy or things like that. We use sharding at database level. So we already are building our applications to scale natively. So all of these reasons made us conclude that we don't necessarily need a distributed file system. Now, having all that said, this doesn't mean that CStore doesn't scale. It's just not distributed in the sense that it's spread out across multiple nodes. So CStore itself will scale up to 228 bits, and it can achieve millions of IOPS in capacity. So now that we know what CStore is not, what is CStore? So CStore is a new storage engine that brings the enterprise class features for containers. And enterprise class features to us means things like snapshot clones, compression, replication, and data integrity. It's also a key enabler for CMotion, for which we will have a demo very shortly. And this is basically our ability to move data efficiently and incrementally from cloud to cloud. Now, with incrementally, I mean, if you have a copy of your data, you send it over to, let's say, from Amazon to Google, and you can use the same baseline send that you did before to send the delta over to the other way. So one could argue that it is kind of like rsync in a way, except that it works at a block level. CStore is always consistent on disk. The way that we achieve this is by using transactions. I'll go over that in a little bit more detail in a couple of slides down the road. Data integrity and encryption, crucial for cloud deployments. Obviously, encryption at rest is a no-brainer. But data integrity is something that is overlooked very easily. And with data integrity, we mean that we will checksum each block that we put on the disk, not just like the metadata as in the extended for file system, but metadata and data are checksums as we write it down. Online expansion of existing volumes. So your database is growing out of its persistent volume claim. You can basically just online add additional storage to that volume without losing any functionality or disruption. Cloud native design versus cloud washed. So what I mean with that is that we did not take an existing solution and put some container lipstick on it and say, hey, we run in the cloud. So we really reimagined how storage should be used for cloud native apps on premises, but also in the cloud. So can I have the next slide, please? Thank you. So this is basically a high-level overview of how it looks. This picture, if you are known with the OpenEBS project, may look familiar. So we have the controller, which serves out the interconnect. In this particular case, we today only do iSCSI, but we are looking into iSer, which is iSCSI accelerated through InfiniBand, and also NMDE over Fabric. And if the community has interest in this, we can also look into the NFS file type like implementations. So the way that it works effectively is that the controller receives the I/O from the application and then forwards the I/O to the underlying CStore instances, which are your replicas. And these replicas typically live on separate nodes, and ideally they're also rack aware and things like that. So when one of the replicas dies, there is no problem. So it is copy on write. So CStore never overwrites data on disk. It will always try to find an unused block and put the new data there. The interesting thing to note here, and I'll get back to that as well, is the red line here. The actual interconnect also runs in a container, and I'll get to that in a minute. Can I? Did I do that? Oh,
no. It was my problem. Just
the transaction slide. Yes. So transaction. So I briefly touched on it already. So what does it mean to have a transactional file system, data engine, what have you? So basically, each write is assigned a transaction number, and these transaction numbers are grouped into transaction groups. And the reason that this is happening is that we want to have optimal bandwidth. And the latest transaction number points to the live data. So if you write 10 IOs, all those 10 IOs get an individual transaction. These 10 IOs get a transaction group number. And then this transaction group number is basically your current view of the data. And this allows us to update the data atomically. And that basically means that all the 10 writes succeed or none of them succeed. If write IO 8 has failed somewhere down the road, we will simply not update the new transaction number, and you will still have the view like if those writes never happened. And the copy on write methodology is the groundwork that enables this. So based on that, on those transactions, we can also create snapshots. And with those snapshots, we basically look between two different transaction group numbers and basically construct a delta between what was there in this snap and what was there in that snap. And this delta is something that we need to send over. And this is basically the foundation of CMotion that will send the blocks that have changed between two transaction groups. Now, one interesting thing to note is that all of this happens in Userspace. So there is no kernel dependency. And this is really, really much needed for a cloud-to-cloud business, because if I run on Google Compute Engine or on Rancher or whatever cloud provider you have, you cannot depend on any kernel features, because the provider that you are migrating to might have a different kernel version or might not have the particular patch. The thing that you don't want to do in the cloud is basically manage your own kernel, and for every instance that you spin up, first build a whole kernel from scratch, download all the software, start building it and inserting the kernel module. And you also don't want to taint your kernel, possibly by injecting non-GPL based licenses, because the Linux community might not be as forthcoming to help you. And one important other note is that due to the atomic updates, the data is always consistent on disk. I mentioned that already, but it also makes CStore self stateless, right? So even though we are persistent data, the engine that puts the data persistently on disk is stateless. And this is because we respect the contract between the client application that is issuing the IO and the actual storage system that runs in a container. So basically what it means, when you say synchronous write this data, when you get the acknowledgement, the data is persistently stored on disk, 100% guaranteed. If you do not get the acknowledged, data is not put on disk, and the application needs to retry. So please, Uma, next slide, and we will go into performance a little bit, because as you may know, if you do a file system in kernel, for example, you do not have to copy data around. So typically data comes in through the network card, the kernel grabs the packets from the ring buffer, puts them in whatever buffers internally it needs to, and then shoves them straight to disk. Now, obviously, as we are in Userspace, this won't work. So how are we going to solve that problem? I'll explain how we do that. But there is another interesting trend emerging, and that is if we look at low latency SSDs, and we have 100 gig network cards coming around, it kind of looks like that the kernel itself is becoming a bottleneck in achieving high throughput numbers. And if you take, for example, a 10 gig NIG, it has a huge amount of packets that it needs to process per second. And per packet, the CPU only has a couple of cycles per NIC to do that, right? So just to give you an idea of how busy your CPU is just by processing networks or latency device, low latency devices like SSDs when it's running full throttle. And the other thing is that frequency basically stays the same over time, and core count goes up. And I don't know what type of desktops you use, but if you buy the latest Apple machine, I think it already comes with 20 cores, right? And when you look at your system monitor, you will see that a certain amount of cores is absolutely idle. And this is because the software that you are running typically was not designed when hardware CPU cores were that cheap and available. So your software is not designed to utilize all those cores. And the final piece is that the hardware trends, I actually already mentioned this, but the thing that I wanted to point out is that you can get a white label box in a 1U chassis that can already do, on paper at least, 17 million IOPS. And this is a staggering amount, right? I would like to see the first person in a container that needs 17 million IOPS for his particular workload. That is just a huge number. I won't say it won't happen, but we're a long way there. So hardware trends enforce a change in the way that we do things. And this circles back to the reason that we did not build a distributed file system as well. So let's look a little bit in terms of numbers. So these are numbers coming from Intel. I apologize for the poor graphics here. I now only see that it's a little bit faded out. But the x-axis shows you the number of SSDs, and the y shows you the number of IOPS times 1,000. And you can see as we add more SSDs to the system, IOPS don't increase. And this is because the kernel is actually owning all the hardware, and the kernel has to do all the work. And the kernel has all these locks in the system for very good reasons, but it doesn't allow the system to scale linearly as it does, as you can see in the light blue graphs. The graph on the right is a very, the graph on the right is a similar picture for a networking side of things. So we have the grayscale where the kernel handles all the packets and all the trafficking and the TCP/IP stack. And on the right, we can see a user space application dedicated to doing this. So the next slide is about, okay, so how do we do that, right? I mean, okay, nice claims, but can you actually make it work? And this is something that we are working hard on very actively at this point. And the solution obviously is to bypass the kernel subsystems altogether and run everything in user space. So the way that it looks is that instead of having your container issue the IO to the kernel, what you basically do is you issue the IO to another container, which we call the IOC, the IO control container. And the IO control container has direct access to the hardware resources and puts the IO on disk or out of the network card for you. And the way that it works is that you basically memory map the network interface card register rings into user space, right? So you basically have direct access from user space to your network card. Likewise, for the NVMe devices, you have the PCI bars where the kernel typically writes its data in, directly mapped to user space. And between that, there is a piece of software which is a lockless message passing between cores. So imagine you have a server, 20 cores, 4 cores will be dedicated to IO, who will communicate lockless and message passing between the cores, have direct access to your network cards and your NVMe devices. And the technology that makes it available so that we can actually run this thing in user space is what we call pull mode drivers. These consume 100% CPU, so instead of having cores being idle, you will have certain amount of cores, and you can select how many, running 100% CPU, constantly checking, hey, is there IO? Is there IO? Is there IO? Instead of having the kernel being interrupted all the time. Now, the kernel, the Linux kernel, recent versions, I believe 4.9 something, does have pull mode drivers itself, so you can have your kernel be 100% busy, but obviously that's not necessarily what you want. The final piece here is that we borrow from VM technology because we need, one way or the other, connect your container to our IOC container. And the way that we achieve this is using vhost and virtio SCSI. You may have heard about these technologies coming from the virtualization space. These technologies don't necessarily have anything to do with VMs themselves. They are just a protocol, and a protocol designed between two processes communicating in a SCSI type-like manner. So we are re-implementing or looking at re-implementing these constructs between containers to get the highest performance out there. And we will eventually outperform the kernel while doing so. So the last slide is a summary, just to make a recap of what I said, because I think there's a lot of information there. So CStore provides the enterprise class features like your friendly neighborhood, insert your vendor storage system from a container per pod, right? Provides data integrity features missing natively in the Linux kernel today. So there is no production grade file system, block layer, what have you, in the Linux kernel available today that allows you to do this. Provides the ability to efficiently work with data by use of copy on write. We bypass the kernel for IO to achieve higher performance than the kernel can deliver. cloud native design using cloud native paradigms to develop and deploy this. So everything is controlled to everything Uma mentioned before. And lastly, from a DevOps perspective, which is probably the most important, is that it removes friction between developers and storage admins. So, and with that, I would like to open up for questions a little bit, if there are any. Thank you.
Yeah. Maybe we can just revisit the question from Viet. Jeffrey, just summarize the answer for him.
Yes, so his question was, and correct me if I'm wrong, is that which file system are you using to basically do this? And so the answer is CStore. And then the second question, perhaps based on that, is okay, so is this something new? It is not necessarily new. It is something that, as Uma mentioned, the company behind the OpenEBS project is CloudByte. CloudByte is a company that has been doing enterprise storage for many, many years, and we are borrowing existing technology from that company, basically bringing that into the open source space world. If there are any specific questions around, okay, so how does this work? Can I get more information? Can I get more detail? You can find me on Slack just as anybody else from our company, and ping me there, and I'll be happy to go into more detail, talking about the underlying methodologies that we use. For example, we are not developing the Pulmo drivers ourselves. We are leveraging existing technology that is available today. Things like DPDK and SPDK are available to us, and we are making use of that. And we are closely working with Intel, for example, on achieving this. So feel free to pop me any question on Slack about that.
Thank you, Jeffrey. And just to add on top of that, the current release 0.5 and upcoming release 0.6 will continue to have the existing storage engine, which is Longhorn based, and the CStore is being actively developed internally. It will be open sourced to the community pretty soon.
Yes, absolutely. And so the reason that it's not open yet is because, as you can imagine, probably heard, it is something that is rather difficult to set up properly, and we want to give people a jump start so that they can actually use it and then contribute to the project. So once it is in a state that we feel comfortable with sharing, people can jump on, download it, use it, send PRs and what have you.
Right. Thank you, Jeffrey. So in the interest of time, let's get started with CMotion Demo. I'm pretty excited about it. I'll let Pius do the demo. Just let me give a very quick view of what we are going to do. Here is the setup that we have. As we discussed, My Online CMotion is a feature using which you can move your Kubernetes pods from one cluster to another across clouds if needed, right? So to demonstrate that ability, we have 3 Kubernetes clusters, 2 on Google Cloud, 1 on Amazon. The 2 in Google are actually across 2 zones. So one is in US Central, the other one is in Europe East. And we have named the clusters as Austin, Denmark, and US East, or Mule Master, right? So we have a Jenkins pod, which is actually building a CI/CD pipeline. It's just based on a GitHub commit. It just runs a build, and we show that which is being run on top of CStore for the data, and in Austin cluster, and then we move the Jenkins pod all the way to the other geographic zone in Europe, and then you will see Jenkins continues to run what it was doing. All the data has been data consistent wise moved to the other side. All your data is intact, and you can continue from where you just where you were before moving. And similarly, we can do that from Europe East to Amazon, and Amazon back to US Central. So you can keep continuing. We'll just probably, in the interest of time, just show one or two moments. Back to you, Faiz, and probably will make you the presenter. I'll just show. Let's go back and do a review. So we have 3 clusters here. The first cluster is on Amazon. It's the second cluster and third clusters on Google. As you can see, Austin and Denmark clusters are running on Central and Europe West. The actual pod, Jenkins pod, is running in Austin. Now we go back and do a couple of builds. We did build number 8 and 9. We can build one more. It's still running on top. Let's do one more build. Let's do one more build on Austin cluster, build number 10, and just to show that it's an active cluster, active pod, and Jenkins pod. And now we go and move this pod, which is running in Austin, to Denmark. And what Pius did here is he's just prepared a pod, CStore pod at Denmark, and now we're going to move this Jenkins pod from Austin to Denmark cluster, right? So that's the source, Austin. So as Jeffrey was mentioning in the overview of CStore, CMotion is very similar to rsync across pods, except that it's at a block level. The data atomicity and transaction based IO will be performed, and you will see 100% guarantee of your data being available on the destination, irrespective of the network failures. If it happens, it'll restart and make sure that your stateful application data is available. And you can actually see on Google Cluster right now that while we are migrating, the Jenkins pod that is running in Austin is actually going to come down, and then going to come back up on Denmark. As you can see that it's still in the process. It takes the amount of time to move this data is really dependent on the time it takes is dependent on the data it has. And right now, the pod on Austin is going down, and the pod on Denmark is actually coming up. And once it's up in the next few seconds, we should actually be able to build the Jenkins on Denmark, right? So let's go there. So you can see that it has actually gone down at Austin, and now we are going to see an application running at Denmark. It's up, and you should be able to make build number 11, 12, 13 here. So all the data is intact, and we did build 10, and then we can continue to do one more build number 11, and then you can demonstrate the same thing going back and forth across the clouds. So that's the demo we want to show. It's a bit rough, but it has the complete functionality, and it is a tech preview version of the CStore, the CMotion feature. And you can see that Maya C is really a Maya CMotion command. It's actually running on Denmark. So hopefully that was useful, and probably I can take some questions on the chat. You can actually show the Jenkins pod now totally running on Google cluster. Just refresh it. It should have gone down and then come back up here, right? So it's totally running on Denmark Maya seamless Kubernetes integration. And once it's up and running, we will be using Kubernetes Federation features very soon, and to seamlessly integrate with all the latest capabilities of Kubernetes to manage the pod migrations across the clouds. So that's the demo. Thank you, Pius. And any questions that I can take either on the demo or Maya Online or CStore, Jeffrey is still here. He'll be happy to help you on that. And Maya Online is free for basic usage. If you're OpenEBS user, you can have centralized metrics and operational support. Feel free to sign up. All right. Nishant, any questions coming up?
No, sir, no questions for now.
All right. Thank you, team, and looking forward to continuing the communication on the Slack channel. And we'll be running this session again at 11 a.m. PST, about 12 hours from now. And this session, Hangout, will be recorded and posted on the OpenEBS site, and we'll be updating the location of the video on the Slack channel. Again, thank you very much. Thanks for taking time. We'll be seeing you soon on Slack.
Thank you. Bye-bye. Thank you. Bye-bye. Bye.